Now we come to chapter 6 module 2. In this chapter we shall consider some examples to find out Fourier transform of some simple functions. We have learned that Fourier transform of a function small f(x) which is denoted by curl f of f(x) or capital F(s) is given by curl f of f(x) which is a function of s, that is equal to 1 by root 2 pi integral minus infinity to plus infinity small f(x) e to the power I s x dx, and its inverse transform is given by small f(x) is equal to 1 by root 2 pi integral minus infinity to plus infinity curl f of f(x) e to the power minus I x s ds. With this information, we shall consider the following examples to obtain Fourier transform of some simple functions. We come to example 1. Find the Fourier transform of f(x) where f(x) is equal to 1 when x lies in the interval minus 1 to plus 1 and 0 otherwise. The Fourier transform of small f(x) denoted by curl f of f(x) which is equal to 1 by root over 2 pi minus 1 to plus 1 into e to the power I s x dx. Here Fourier transform we have defined in this way. So, f(x) you can see that it is defined as in the interval minus 1 to plus 1. f(x) is non-zero in the interval minus 1 to plus 1. So, that this integral starts from minus 1 to plus 1, and this is given by 1 by 2 pi e to the power I s minus e to the power minus I s divided by I s, which is equal to root over 2 by pi sin s by s. So, this is the Fourier transform of the given function. Remark, if we write the inverse transform, we will get back the function itself. So, inverse transform is given by 1 by pi integral minus infinity to plus infinity sin s by s e to the power minus I s x ds, which is equal to the given function, that is equal to 1 when x lies in the interval minus 1 to plus 1 and 0 otherwise. If we substitute x equal to 0 here, we obtain the result integral minus infinity to plus infinity sin s by s ds equal to pi. Next we come to example 2. Find the Fourier transform of f(x) where f(x) is given by e to the power minus a mod x where a is positive. Now, the Fourier transform of this function is given by curl f of e to the power minus a mod x. This is equal to 1 by root over 2 pi minus infinity to plus infinity e to the power minus a mod x e to the power I s x dx. So, the integral from minus infinity to plus infinity can be divided into minus infinity to 0 and 0 to infinity, where in minus infinity to 0 the function e to the power minus a mod x is equal to e to the power a x, and in the interval 0 to infinity this function e to the power minus a mod x becomes equal to e to the power minus a x. So, writing this, we can simplify to obtain the Fourier transform of e to the power minus a mod x as given by this expression, that is 1 by root 2 pi integral from 0 to infinity e to the power minus a x plus I s x dx plus 0 to infinity e to the power minus a x minus I s x dx. This integral can be evaluated to give 1 by root 2 pi into 1 by a minus I s plus 1 by a plus I s, which can be simplified to give root over 2 by pi a divided by s square plus a square, where a positive, and this is the Fourier transform of the given function f x equal to e to the power minus a mod x. Now, we come to another example, that is example 3. Find the Fourier transform of f x where f x is equal to minus x square by 2. The Fourier transform of this function is written as curl of f of e to the power minus x square by 2. This is equal to 1 by root 2 pi integral minus infinity to plus infinity e to the power minus x square by 2 into e to the power I s x dx. In this integral, we multiply by e to the power s square by 2 into e to the power minus s square by 2. So, that next step becomes equal to 1 by root over 2 pi e to the power minus s square by 2 integral minus infinity to plus infinity e to the power minus half x minus I s whole square dx, which is equal to 1 by root over pi e to the power minus s square by 2 integral minus infinity to plus infinity e to the power minus u square du, where u is given by 1 by root 2 x minus I s. Next we evaluate the integral I equal to minus infinity to plus infinity e to the power minus u square du. To evaluate this, we write I square as integral minus infinity to plus infinity e to the power minus u square du into integral minus infinity to plus infinity e to the power minus v square dv. So, that this becomes equal to double integral from minus infinity to plus infinity e to the power minus u square plus v square du dv. We change this integral to polar coordinate, so that this integral becomes 0 to infinity 0 to 2 pi e to the power minus r square r d theta dr. Here u is r cos theta, v is r sin theta. So, that u square plus v square is equal to r square, which gives integral from 0 to infinity e to the power minus r square r dr into integral 0 to 2 pi d theta, which is equal to half into 2 pi, that is equal to pi. So, that I is equal to root pi. That means, we have obtained I square equal to pi. So, I is equal to root over pi. Hence, the Fourier transform of f x equal to e to the power minus x square by 2, this is equal to, by substituting root pi for this integral, we obtain this as equal to e to the power minus s square by 2. So, it is interesting to know that the function f x equal to minus x square by 2 has the Fourier transform capital F s and which is equal to small f s, and this is the self reciprocal in the sense that the function is its own Fourier transform. Now we come to example 4. Find the Fourier transform of f x where f x is equal to 0 for x negative and f x equal to e to the power minus a x for x positive and also a positive. We are to find the Fourier transform of this function. Fourier transform of f x denoted by curl f of f x is equal to 1 by root over 2 pi integral 0 to infinity e to the power minus a x e to the power I s x dx. This integral can be evaluated. So, we get the Fourier transform of f x as 1 by root over 2 pi 1 by a minus I s. Now, we consider another example, example 5. Find the Fourier transform of f x where f x is equal to sin x for x lying in the interval 0 to pi and equal to 0 otherwise. Here the Fourier transform of f x is given by root over 2 pi curl f of f x, that is equal to integral 0 to pi sin x e to the power I s x dx, that is equal to 1 by 2 I integral 0 to pi e to the power I x minus e to the power minus I x e to the power I s x dx. This integral can be evaluated and we get the result 1 by 2 I e to the power I s plus 1 x by I s plus 1 minus e to the power I s minus 1 by I s minus 1 from 0 to pi, that is equal to minus half in e to the power I s plus 1 pi minus 1 by s plus 1 minus e to the power I s minus 1 pi minus 1 by s minus 1, which is equal to minus half minus e to the power I s pi plus 1 by s plus 1 plus e to the power I s pi plus 1 by s minus 1. So, that Fourier transform of f x is given by 1 by root over 2 pi e to the power I s pi plus 1 divided by 1 minus s square. Remark, this integral can also be evaluated in the different manner, that is the Fourier transform of f x contains this integral which can be evaluated in a different manner, that is we simply apply integration by parts to get I equal to minus cos x e to the power I s x from 0 to pi plus I s integral 0 to pi cos x e to the power I s x dx, which is equal to e to the power I s pi plus 1 plus I s into sin x e to the power I s x, x ranges from 0 to pi minus I s integral 0 to pi sin x e to the power I s x dx. This can be simplified again to obtain I equal to e to the power I s pi plus 1 plus s square I. So that I is equal to e to the power I s pi plus 1 divided by 1 minus s square. So, this is the Fourier transform of the given function. So far we have considered 5 examples where we have learned how to obtain Fourier transform of functions. In the next 2 examples, these are interesting examples. Here we will find out Fourier transform of some simple functions. We come to example 6. Show that Fourier transform of the function f x equal to 1 minus mod x for mod x less than 1 and 0 otherwise is capital F s, which is the Fourier transform of small f x. This is equal to 2 into root over 2 by pi sine square s by 2 divided by s square. Hence, show that integral minus infinity to plus infinity sine x by x whole square dx equal to pi. So, we find out first the Fourier transform of this function f x. So that root over 2 pi capital F s is equal to minus 1 to plus 1 where the function is defined, integral minus 1 to plus 1, 1 minus mod x e to the power I s x dx. Now from minus 1 to 0, this function is 1 plus x e to the power I s x, and from 0 to 1 this integrand is 1 minus x e to the power I s x dx. So that these two integrals can be simplified and we obtain 2 into integral 0 to 1 1 minus x cos s x dx. So, we integrate by parts, this is a simple integral and we get 2 into 1 minus x sine s x by s from 0 to 1 plus 2 by s integral 0 to 1 sine s x dx. That is equal to 2 by s square minus cos s x from 0 to 1, and that can be simplified as 2 into 1 minus cos s x by s square, which is equal to 4 sine square s by 2 divided by s square. So, the Fourier transform of the given function is 2 into root over 2 by pi sine square s by 2 divided by s square. So, we have obtained the first part of the example. Now, we have to show the second part. For second part, we note that the Fourier inverse transform gives back the function itself. So, f x is curl f inverse of capital F s, that is equal to 1 by root 2 pi integral minus infinity to plus infinity f s I s x ds. Putting x equal to 0, we obtain f 0 equal to 1 by root 2 pi integral minus infinity to plus infinity capital F s ds. That is f 0, if we can see the function f 0 is equal to 1. So that 1 is equal to 1 by root 2 pi 2 into root over 2 by pi integral minus infinity to plus infinity sine square s by 2 by s square ds. Here we have substituted the value of capital F s, and this is equal to 2 by pi integral minus infinity to plus infinity sine u by 4 u square into 2 du. which can be simplified as 1 by pi integral from minus infinity to plus infinity sin u by u whole square du. So, we deduce that integral minus infinity to plus infinity sin x by x whole square dx, that is equal to pi. Next we come to example 7. This is a very interesting example. We are to find out the Fourier transform of f(x) equal to 1, very simple function. X lies in the interval minus infinity to plus infinity. Now, recall that Fourier transform of a function defined in the interval minus infinity to plus infinity exists if the integral minus infinity to plus infinity mod f(x) dx is finite, that is the function f(x) is absolutely integrable, that is the condition of Fourier integral theorem. But when f(x) equal to 1, this condition is not satisfied. However, one can still define the Fourier transform of f(x) equal to 1 by considering the notion of generalized function delta x. This delta x is defined as delta x equal to 0 for x not equal to 0, and delta x has the property that minus infinity to plus infinity integral phi x delta x minus a dx equal to phi of a, where phi x is some ordinary function. This integral has no meaning in the usual sense and is used to define the generalized function delta x. Thus, if we take a equal to 0 and phi x equal to e to the power minus I s x in this integral, then we have integral minus infinity to plus infinity delta x e to the power minus I s x dx equal to 1. So that using the property of delta function, we see that this is the Fourier inverse of delta s, and that is equal to 1 by root 2 pi. So, we write Fourier transform of 1 as root over 2 pi into delta s. So, this is the Fourier transform of the function f(x) equal to 1. Thus, we have concluded module 2 of chapter 6. In this module, we have learned how to find out Fourier transform of the function f(x). This includes a very interesting example, that f(x) equal to 1. Although in this example we have seen that f(x) does not satisfy the condition of Fourier integral theorem, yet its Fourier transform exists in the sense of generalized function.